Hello and welcome to this series of lectures where we focus on how we can measure and sense phenomena related to the solid Earth. Before we start looking at particular instruments and measurement techniques, we will discuss a little bit about what we actually mean when we talk about the solid Earth and which phenomena we're expecting to see. Let's start with the Earth as one would see it from space. At a first glance, it appears to be a sphere. But if we would measure its size more accurately, we would find out that the Earth is flattened at the poles and has bulges at the equator. The distance from the center of the Earth to the equator is about 21 kilometers longer than the distance from the center to any of the two poles. If we take the mean over all distances on the surface to the center, we would get a value of about 6,370 km, which already shows that the 21 kilometer bulge at the equator is relatively small compared to that value. In many Earth science applications, we can ignore the fact that the Earth has that bulge and treat the Earth like a sphere. Some applications, however, for example those related to measurements of the figure of the Earth, require us to use the correct shape. To explain why a bulge can form at the equator of the Earth, let's take a look inside our planet. We would then see that some regions are rather fluid instead of being solid like a rock. As the Earth is spinning, fluid masses tend to move away from the rotation axis and thus causes the bulge at the equator. So let's imagine that we go on a journey deep inside at the center of the Earth. On this journey, we could categorize the Earth interior in two ways: by chemical composition or by physical properties such as density and state of matter. Let's start with the classification according to chemical composition. Starting at the very center, we would find a solid ball made of iron and nickel, which has a radius of about 1,200 km. This is called the inner core. If we go upwards, we would enter the liquid outer core, which is composed also of iron and nickel. After the outer core, we would enter the so-called mantle, which is the silicate rocky shell with an average thickness of 2,900 km that accounts for almost 85% of the Earth's volume. Reaching the outermost part of the Earth, the crust, we would categorize it as a solid shell, which is built up by compounds containing mainly oxygen, silicon, and aluminium. If we take the same journey again, but now look at the physical properties, we can again split between the solid inner and liquid outer core. The movement of this liquid region actually is the cause of the Earth's magnetic field, which deflects most of the solar wind, whose charged particles would otherwise strip away the ozone layer that protects the Earth from harmful ultraviolet radiation. Thus, without that liquid outer core, life on Earth would have not been possible. But let's continue upwards, where we reach the mantle. Also, the mantle is mainly solid. It actually behaves like a viscous fluid when seen over periods of millions of years. Also, the mantle reveals more details, which leads us to a separation into three parts: the Mesosphere, the Asthenosphere, and the Lithosphere. The Mesosphere accounts for most of the Earth's volume, but is clearly distinguishable from the rather viscous Asthenosphere. The Asthenosphere can be found in depths between 80 and 200 km. As we have seen, large part of what we call solid Earth actually is not solid at all. The uppermost layer, the Lithosphere, is of direct relevance for us humans, as it is the ground on which we live. In general, the Lithosphere consists of several separate and distinct tectonic plates, which literally float on the fluid-like Asthenosphere. If the plates would only float around, we would not notice much about them, but plates are in contact with each other. The location where two plates lie next to each other is called a plate boundary, and these zones are usually strongly related to geological events such as earthquakes, volcanoes, mountain building, ridges and trenches in the oceans, etc. In general, Tectonic plates can include continental crust or oceanic crust, but most plates contain both. Actually, what happens if tectonic plates move, but there is another plate next to it? Well, in theory, there are three basic options. First, one could observe a transform boundary, which is seen at places where two plates slide against each other. This process is conservative, which means that plate material is neither generated nor destructed. But the grinding of two massive rocky plates shatters the ground, which is the reason why earthquakes can occur along such boundaries, also called faults. The San Andreas Fault in California is a classical example. The second way how plates can behave is called a divergent boundary, which means that the plates drifting apart from each other because material from below is coming up and pushing them aside. For example, seaforth spreading in the Atlantic Ocean pushes the North American and the Eurasian plate away from each other. Knowing now that plates can grind against each other and that they drift away, it is only obvious that at some place destructive processes need to take place. This third type of zone is called Convergent Boundary and describes a situation where one plate moves underneath the other one. As this process is not always going that smooth, earthquakes are a natural consequence. Moreover, as the Asthenosphere is quite deformable, it is possible that parts of the Lithosphere can penetrate it and dip deep into the Mesosphere. Since temperature is increasing with depth, part of the dipping lithosphere melt a deeper region, which can cause plumes of hot magma to rise and eventually reach the surface. This effect is the reason why we find volcanic activity in regions like Hawaii, which is far away from continental boundaries that cause volcanic activities normally. Earth sciences have contributed a lot to the understanding and monitoring of plate movements on local, regional, and global scales. In this course, we will focus on those techniques which are being actively dealt with here at Chalmers University. Thanks for watching and see you next time.